Hey there, camels. Today I want to continue our exploration of locals. So previously we've gone through local parameters and variables and return values. We talked a little bit about how local and global are modes. Today I want to talk about inference and the way that the OCaml compiler sort of figures out how all of this should work. So let's start out with our usual setup here. Whoops. Okay, is this working? Oh. You'll see there's a little sneak preview of what's about to happen. Okay, so we have this. Now, when I start writing local variables inside of a function, we have to then figure out whether they should be global or local. So here's an example. So I have this x. It's not used, but we have x. Is that going to be global or local? Well, if I try to compile this, we don't know. There's nothing that tells us right away in this output here. We know that f is from unit to unit, but what about this x? Now, at first you might think, well, that doesn't really matter. And in some sense it doesn't. It's just like it doesn't really matter right now that whether x is a string or not. But as we build a bigger program, we want to have an idea of how this is all going to really play out. So one way we can get perspective in this is to ask the OCaml compiler for more information. Now, what I'm about to do, I don't recommend that you do on a regular basis as you're doing programming. This is more for demonstration, but you can do it while you're programming. And that is to pass d-typed tree down here. So if I pass d-typed tree, then it will print out sort of the intermediate representation that the OCaml compiler is using that has all of the types in it. So whoops, let's see what happens when we do that. And there's like a whole bunch of stuff. The output format here is really not very good, but that's okay because this is really just, it's really intended just for debugging the compiler. What we see here though is that this x, here's the x that I've bound up here. And we can see right after it, it lists the alloc mode, which in this case is mode var. Now, if we think about it from an implementation point of view, well, what does it have to do? It has to say, well, I don't know what the mode of this x should be, so I'm just going to invent this mode var variable, and then we'll try to solve the variable. So if I make a change, if I return the x, this would be an escape from the function's region, and now I try to recompile. If I scroll up, I see, oop, now this one is global. We know that this one has to be global. Conversely, if I put a local annotation here on x, and then let's make sure it doesn't escape, and I recompile, now when I scroll up, we see that the alloc mode is local. So we can affect this. So it really internally, it has to be doing this inference to figure out what's going on. If I don't have any annotation and it doesn't escape, what does it do? Well, it does sort of whatever is best. It is going to make a decision, but it actually makes that decision after type checking is complete. In this case, what it's going to do is it's going to prefer local because, as we'll see in a future video, local gives us better allocation behavior. So in the end, right, this whole scheme about locals, yes, it gives us these extra safety properties. Sometimes that's very nice. The reason that this whole idea was created within Jane Street was to allow parts of OCaml programs to be allocated in using a stack discipline instead of on the heap requiring garbage collection. So local is in some way better than global. Okay, so that's inference for a local variable. But what about more generally? So more generally, we always try to be as permissive as possible. So the most permissive thing to do in a parameter is for it to be local. And the reason for that, as we saw last time, is that global is a submode of local. And so if we have a local parameter to a function, then that means that that function can accept locals and it can also accept globals. So let's just look at that for a sec. So if instead of f just taking unit, let's say f takes x. Oh, and what can it do? Maybe it prints the value of, oh, that's going to cause escape because printing doesn't know that it actually could be local if it wanted to be. Let's just ignore x. It's kind of silly, but if we have this function here, let's compile. We don't need type tree anymore. This is going to be alpha to unit, but I just said that we're going to prefer local parameters. Well, something a little bit sneaky is going on here. And the way that we're going to discover the sneaky thing is we have to wrap this in a module. So we're going to have module M, and this is going to have some signature, which we'll sort out, and then it's going to have a struct. Okay, so we now have our structure. That should still work. Yes, it does. But the question is, what type can I give f here? So I can give arrow unit. That works just fine. But I can also give local arrow unit. So what's really going on here? So maybe as you're familiar from OCaml programming, the way that signatures and structures work here in modules is that first the signature is sort of checked, but that signature is not used while type checking the struct. So we go through, we figure out everything that there is to know about the struct, and then we check after type checking the struct, does this structure match this signature? And so what that means is that when we are inferring the type of this f, just forgetting about everything else in the file, just looking at this, when we're inferring the type of this f, this is actually going to be inferred to take a local parameter, because that matches then this signature. So earlier, when I didn't have this whole struct, we saw that actually f did not have a local parameter. Actually, I'm curious. I don't know what's going to happen here. If I don't have a signature, what are we going to see? So here we also see that there's no local. The reason for this is that when there is no MLI file, when we have the type of a module, in this case, this local module, this whole file here, when we have the type of a module and there's no signature for it, then there's this defaulting step which gets rid of all of these local underscores. And that's basically so that there's not strange things that happen in projects without MLI files. We could probably do a better job of this, but this is what happens today. The thing to remember though is that when we see just this definition, so here x is not escaping, and it can be somewhat more complicated than just ignoring x. Right? I could pass x to other functions that don't escape. Like if I have let don't escape, and this can take a local, and then, well, this won't do anything. But here I can call don't escape, and then let me bring back my signature. And this still works, right? So it doesn't just have to be ignored. We can do manipulations. We can do some arithmetic and such. It's a little hard to make examples here because the various operations that I might do, the standard library doesn't have support for locals really, and so every little thing that I might actually try to do is going to force things to be global and then sort of disrupt my examples. But I promise you can do interesting things here. Let's see, where were we? Here in this f, again, we are inferring this local type, which is why this works. So we might wonder at this point, how does this work? Right? We've seen that it does. And that's because when we're checking the signature of one module against another, we allow some flexibility. So this f is inferred to have a local parameter. That means that it promises that its parameter doesn't escape. But as we talked about last time, local on a parameter is a promise about the implementation of a function. So we can just forget that promise. And that's what's going on up here. And so the check that sees is the type of this module, is the inferred type of this module, which does mention local, is that a subtype, a submodule type of this module signature up here? Well, it is, because we can just forget about that promise, and that's fine. Okay, so here we can see that we're doing inference to prefer local parameters. Here I haven't done an annotation here on this x, and yet we're inferring a local parameter. But the result, we're also going to prefer a global result. And that's because the result is going to be used somewhere else. So when I use that result somewhere else, I might use that in a context that requires global. So, for example, if let's say I have, let's have let g of unit equals hello. So do I want this hello to be a local or a global? Well, it might matter because maybe after my module here, so now I need to add this to my signature. So I'm going to say g is unit to string. So after my module, then maybe I want to do something like print it. And let's see, does that work? Oh, that probably doesn't work because I need semicolons or something. Let's just do that so we avoid that weirdness. So, unbend. Yes, I need my m dot. Silly. Okay, so this is now okay again. But if we had inferred g to have, and actually let's just look at, well, then there's inference. It's a little hard to sort of demonstrate this actually. If we had inferred g to have a local return, then we wouldn't be allowed to call print nline on it, right? Because local things can't just get automatically converted to global things, right? They have to, they'd have to get globalized to do that. And so within Jane Street, we actually have a globalized PPX that allows you to do that. If you have a local value and you want it to be global, you can do that using that PPX. Here we don't have that, and so this G had better be global. So we want to always prefer to infer a global return value because that's generally more useful. And then because of that, if I put a local annotation here, what's going to happen? I think this won't work down here, but I think the rest of it probably will. Yes, so the print nline fails, but if I comment that bit out, I think we'll be okay. Yeah, and so we're okay here because this is going to infer unit to string, but this local here imposes more requirements of the caller, right? So when you have local on a parameter, that imposes requirements on the function that it doesn't let it escape. When you put local on a return, that imposes requirements on the caller that the caller doesn't let it escape. So I can always impose more requirements on the caller. So I am allowed to write local underscore over here. But, well, I bet it is going to allow it on the other one too. Because yes, it's going to allow it there because that unit is not, sort of doesn't escape either. But if we had something that did escape, let's have something that does escape. So here, this X is definitely escaping. And now, if I said H, and let's see, so H is going to infer a global parameter. And so if I write string arrow unit, that should be happy. Yes, that's happy. But now if I put local here, that's going to be unhappy. And it says that, that there's a signature mismatch in H because the inferred type of H is string arrow unit, and yet I'm requiring it to be local, right? This is now sort of after the fact putting on a new requirement on the implementation of H. That we can't do, right? So we always have to be careful. We can remove locals from parameters. That's okay. We can add locals to return types. That's okay. But we can't do, we can't sort of go the other way around. There's one big exception to this, and that's around ints. So let's look at a few functions involving ints. So if I have let's see, jx equals x plus x. Well, is that escaping? Is that not escaping? I don't really know, right? So it sort of depends on the type of plus. But if I say val j is int arrow int, now we still have the problem with h. Let's get rid of that problem with h. Okay, so here we have val j is int arrow int. Can I just start adding local things? Sure. That's just fine now. So let's challenge this a little bit. So let's, instead of just saying x plus x, because it's a little unclear, like it depends on kind of how plus is. Let's require this to be local. Does that still work? That still works. So I guess plus allows us to use a local thing. But let's also now say that we're just going to store this in a reference. Oh, this value escapes its region. That shouldn't be so much of a surprise. We've said that it's local. But a very interesting thing happens when we know that x is int. Now suddenly everything is okay again. So at first, this violates what we thought we understood, right? Here I have a local x, and yet I'm storing x in a reference, and so that looks like it's escaping. Well, the reason that this is okay is because ints are very special in OCaml. An int is an example of something called an immediate, and it's something that's represented without the use of a pointer. Every type other than int, well, that's not quite true. I guess bool also. There's a few others, but almost every type in OCaml is represented by a pointer. This whole design around locals started as a way of allowing different allocation behavior for local things. And so because this isn't stored by pointer, it turns out that it doesn't need to follow the same discipline as the rest of types. The other way that we say this is that ints can mode cross. So this x here is local, and here it has to be used in a global context, but that's fine because ints can mode cross. So my local int can suddenly pretend that it's global, and that's okay. Another way of saying the same thing is that ints are always global. One interesting thing, though, that's going on is that I do need to put the type annotation in. If I leave out the type annotation and we're just using inference to figure out that x is int, well, then our inference mechanism isn't quite clever enough to use the fact that this plus enforces x to be int, and then that makes this okay. I shouldn't even say it's not quite clever enough. We could probably get that to work, but then it would become very fragile, right? We don't really want information to flow from one part to another this way. That can lead to fragile typing. And so we require you to say somewhere that x really has to be an int for this to be allowed. And so this is a bit of an exception to all of the rules, and it's why in all of the examples that we've seen, I'm using strings, because strings don't mode cross. Right, so ints can always be treated as if they're global. That's also why, even forgetting about the ref, this works, right? I said a few minutes ago that the standard library doesn't really know about locals, and so why should plus know about locals? It doesn't. What's happening here is that the x is mode crossing in order to be passed to plus. So this is a little dissatisfying in that I started this series talking about how local gives us extra safety properties. Well, what if I want safety properties on an int? I can't, and because of this mode crossing. So this is actually something that we're currently working on as a new improvement that gives us finer grained control over what can mode cross and what can't. I mean, nothing that is represented by a pointer would be safe to mode cross, but maybe even things that aren't represented by a pointer we might want to mode cross. There's a few other things with inference that I want to explore in this video. And so actually, though, I think I'm going to reset and start with a blank slate here. And so the other part is that sometimes we can also infer conversions between functions that have different locality. So if I have let f is string to string, and that can be something like this, then if I say let g is string to local string, can I just say that that equals f? Why, yes, I can. From a safety standpoint, this makes good sense. And that's because, again, this local here is saying that the caller of G promises that the result doesn't escape. So I'm just adding another requirement on the caller. That's fine. We should expect this not to work. Whoops, not G, I want to say F. And that's because this local on a parameter is putting an extra requirement on the function. And this f that doesn't say that it upholds that requirement, we can't impose that after the fact. So that's no good. But I can give a different definition for h here. So let's just do something fine. So now we're okay again. What if I go up here and now I say let j, whoops, is string arrow string equals h? How is that? Well, that doesn't work. But actually, this should give us a little bit of pause, right? I said earlier that this local annotation here is imposing a requirement on the implementation. J is attempting to forget that requirement on the implementation. That should generally be okay, and yet it's rejected. So this is actually something, maybe it's been merged, I can't quite remember, but this is something that we can fix. And so this one is safe, and I think maybe by the time you're watching this might be allowed already. But it's something that takes a little of extra work. When things like this aren't allowed, there's an easy way out, and that's just doing some expansion over here. So instead of just saying h, I can say fun x arrow h of x, and then now everything is okay. Just as a counterpoint up here, when I tried to do this, that's not okay, and it really isn't okay. Even if I try to expand this, we're still going to run into trouble. And that's because f really doesn't make the promise. And so saying after the fact that it does is really no good. So there's a difference here. And so what all of this is to say is that there's a little bit of conversion that OCaml is happy to do between these different arrow types with different localities, but not any, not all are safe. So I think that's enough exploration of inference here. One nice thing about all of this inference is that generally speaking, you don't have to write local annotations in terms. And so in a lot of examples, we've seen things like, I'll say let local x equals stuff. You generally don't ever have to do that. That inference will sort of figure it out for you, but it's good for to require. It's just like you don't often have to put type annotations on things. Bottom line is that inference tends to work fairly well with a couple of caveats that we've seen today. Anyway, thanks very much for watching. Hope this has been interesting. Bye.